Tour is a creationist. Did you know that's the last derogatory term that they're allowed to use in the university? They can't talk about my religion, they can't talk about my ethnicity, but they can call me the dreaded creationist. Have I talked at all about creation in this? I haven't mentioned anything, it's just science. But they will use the term creationist, therefore think that they don't have to address this. Okay, scientists are still clueless on life's origin, and I'm going to make an appeal tonight to my colleagues. And they're not here, but this is going to go up on my YouTube channel, Dr. James Tour, and it probably in a couple of weeks we'll get it up there. But this is an appeal to these particular people: Professors Lee Cronin, Steve Benner, Jack Sostek, Gerald Joyce, John Sutherland, Nick Lane, Duran Lancet, David Deemer, Clemens Reichert, Bruce Lipschitz, Nicholas Hood, Ramanathan Krishnamurthy, Neil Devaraj, and Matthew Panner. So come and let us reason together. These investigators all work in the area of origin of life. And my appeal is specifically to you tonight, because I don't understand the chemistry, how the chemistry that's being done is really going to get us toward life, and how we're going to do these things, because there's just so many barriers. So you really ought to be helping me, and you really ought to be showing me how this leads, how this is a prescription, something that will map us out toward getting to life. And so I'm going to share with you some of the problems. And so to you researchers, bear with me, because I'm going to bring this audience through some definitions and give them some background, and then we'll get into the specifics of where there really are challenges. Okay, so here's some definitions. Abiogenesis is the origin of life from non-living matter. To construct any convincing theory of abiogenesis, we must take into account the conditions of the earth about 4 billion years ago. That's not my definition. That's a textbook definition. If you do not believe in the physical resurrection of Jesus Christ, send me an email, tour@drjamestour.org, and we will get together, and I will share with you about why I embrace the resurrection of Jesus. Prebiotically relevant means that we're restricted to materials and procedures and conditions that might have been available on an early Earth. So on an early Earth, you wouldn't have had laboratories, you wouldn't have had people to control the addition of things, you wouldn't have chemical suppliers. You just have to deal with whatever happens to be around, and you can't even just gather it up and pull it together. It has to somehow get together itself, just by the wind and the rain, and it has to be able to pull these things together. You have to do that for whatever procedure you have to be prebiotically relevant. Nobody was present at life's origin, so we will never know how life originated. But that's not what we're seeking to answer. What we are seeking is an experimentally verifiable hypothesis as to how life might have originated. We'll never really know. But all we really want to do is say, how might life have originated scientifically? Scientifically. How might this have occurred? Because that's what that list of gentlemen that I showed you are trying to answer in their origin of life studies. And you can't just throw stuff out there. You can't just say, well, maybe this went to this, and this went to this, and this went to this. You hear scientists do that sort of nonsense all the time. It's really nonsense. It's really fairy tales. And then you point out to them why that couldn't work. And, oh, well, then it could have done this. This is just nonsense. You see that they're just grasping. It's not real. That's not the way other areas of science are done. When you say things, there has to be some hypothesis behind it that's verifiable. You test something in your laboratory under what might have been simulated prebiotic conditions, and you see if it works. That becomes now a verifiable hypothesis. That's what we need to be able to do. Here's another textbook definition of the characteristics of life. Has responsiveness to the environment, growth and change, ability to reproduce, have a metabolism and breathe, maintain homeostasis, and being made of cells, and passing traits onto offspring. And homeostasis is a steady internal physical and chemical condition. Again, this is not my definition. So this is not what is life. That is a question that science does not give us. Science does not answer what is life. The Bible is much better at answering what is life. There are some things that science does not answer well. Some things that it just doesn't answer very well. One of them, what is life? But the characteristics of life, science gives this as the characteristics of life. This is what life looks like. If you have life, all of cellular life, and every bit of life that we know of is cellular life. It's made out of a cell. There's nothing else out there. And so it has to be responsive to the environment. It has to be able to grow. It has to be able to change. It has to be able to reproduce. It has to have a metabolism, and it breathes. And it has this internal state. And for those of you that like thermodynamics, it is a very high energy system, very low entropy. Very high energy, very low entropy, meaning low entropy, it's very ordered. And homeostasis, and it has to pass traits on offspring. And we have to have this condition in which we all live. We have homeostasis where our bodies are working. It's an amazing architecture, what's happening, but we're not even thinking about anything that's as sophisticated as our bodies. This is just a single cell. And this is what the origin of life has to answer. Where did that first single cell, how did that form? Once that forms, then Darwinian evolution can take over. But we need to have the basis. Where did that cell come from? How did that cell come together? So I am not speaking of God of the gaps. That's not what I'm here for. So I am not one to ever say, well, we don't have an answer, therefore God fills that gap. That's called God of the gaps. I never use that argument. I am accused of using that argument all the time. All the time. I'm accused even by some of the men that I showed you their names. I'm accused of speaking God of the gaps. And then I have challenged them to say, show me the quote where I've written that, or show me the YouTube clip. Show me where I have said God of the gaps. And do you know what I get? Crickets. Nothing, because they can't show me, because I've never used that argument. But they like to put that upon me because it's another one of the ad hominem attacks. So I'm appealing to you researchers that I named your names. Don't put that upon me. I am not claiming God of the gaps. Just because we don't know something, we may learn it in 10 years. We may learn how something happened. So I'm not speaking a God of the gaps argument. And if you try to pin that on me, I'm going to challenge you on it, and it's going to be embarrassing for you. Molecules are the language of living systems. This is our alphabet. This is what we deal with in living systems. It's molecules. Molecules are the language of all living systems. Okay, so you have small molecules like this. Here, this is a molecule of glucose. It's a monomeric sugar. And every time you see one of these arrows here, these red arrows, that is a stereogenic center, meaning that it can have a left-handed or a right-handed configuration. And so you have the sugars, you have the amino acids. There are 20 essential amino acids that we use more amino acids than 20, but there are 20 major ones. 19 of those 20 have a stereogenic center. There are nucleotides, which are made up of a sugar, a fructose sugar. Then there is a phosphate hooked on, and there is a base hooked on. So you have to be able to solve the sugar problem before you can make a nucleotide. So we have to solve that one before we can make that. And then this is glycerol, and you have to be able to desymmetrize this in order to make all the lipids. So these are the small molecules. These are the building blocks of the building blocks. Well, what builds us? What builds us is not so much these, but these, the larger analogs of these. So in other words, when we polymerize together the sugars, you get polysaccharides. We are composed partially of polysaccharides. Polypeptides, these are our proteins. These are, you take amino acids, you string them together, and you get polypeptides. We're made out of polypeptides. So all of our muscles are polypeptides. Polynucleotides. This is our DNA and RNA. So this is particularly shown here is DNA. This would be leading to RNA, this particular one. But the nucleotides, you polymerize them, that makes up our DNA and our RNA, which code for information. But they do other things. They can do other things as well, and other things can code. Because whenever you have an arrangement of these molecules together, that's a code. That's bits of information strung together. And those bits of information that are strung together embed information that's stored information for us. And then there's lipids. People say, well, the lipids are really easy to make. They're not that easy to make because you have to desymmetrize this. And these two are enantiotopic, which means they have exactly the same reactivity except to another chiral molecule coming toward it. And the way nature deals with this in living systems is it has enzymes to do that, which are generally polypeptides. And if you say, well, you get the polypeptides first and then you desymmetrize this. Okay, well, where'd the polypeptides come from? That's the problem, and that's what's going on. So you have the lipids. So you need these 4 building blocks constitute our bodies. This is what makes us up. These are the 4 building blocks. These are the tiny pieces that make up the building blocks. This is the language of living systems. It's all chemistry in this way. But molecules don't care about life. Molecules have never been known to care about life. They don't go toward life. This whole idea of molecular evolution, you will hear people talk about molecular evolution. That's another nonsensical term that people have used because molecules do not evolve toward life. Organisms move toward life. Organisms want to sustain life. Organisms want to have offspring. But molecules, the pieces that make them up, they have no brain. All of those molecules I showed you, they have no brain. They don't know to go toward life. You could scream at them all day, go toward life. Do it. They won't do anything. They won't go toward life. They have no brain. They don't know that you want to move toward life. They don't know that. There's no knowledge of that. They don't know to move toward life. So they don't know what's going on there. And so this whole idea that molecules somehow would move toward life is just not true. They don't move toward life. And what I want to do is I want to appeal not to the audience here, although some of you may know, I want to appeal to those experts that I listed their name at the beginning. If I say anything that is wrong, correct me. Go ahead, send me an email, or just make a little video and post it. Or you can come on my podcast, Dr. James Tour, and we'll talk about it. We don't have a debate. We'll just talk about it. Just say, you said this and it was wrong. And if I'm wrong, I'll say, okay, sorry about that. And just show me where I'm wrong. But if I'm not wrong, just say, Tour's talking. I mean, what he's saying is right. All right. And so we need to stop with the ad hominem attacks and just let's talk with one another. Let's just do it. That's why I'm asking you. I'm appealing to you. If I say something wrong here, just point it out to me. All right. Has the public been misled on origin of life claims? Well, this question was asked. It was under simulations of Earth's early atmosphere. Scientists have mixed molecules together in laboratories to produce complex life forms such as frogs. So this was asked. There were a little over 700 respondents, about 700 respondents here, and so 2/3 of the general public thinks that's false. 1/3 thinks that's true. So 1/3 of the general public thinks that scientists have mixed together molecules in a laboratory, and they've made complex creatures like frogs. Right? 1/3 thinks that that's true. Another question was asked. Under simulations of early Earth's atmosphere, scientists have mixed together molecules together in laboratories to produce simple single-celled life forms such as bacteria. 2/3 of the general public thinks that's true. The answer to both of those is a resounding false. Not even close. Not even close. Some of the gentlemen that I showed you their names have said that we're very close to doing this. We're very close to doing this. And I'm going to show you today that they're wrong. They have backed off from saying that. And so I think that we've had an effect here by calling them out on this. They don't say that anymore. Recently, I haven't heard them say that anymore. But 2/3 of the general public. So this is how misled the general public is. They think all of this, they think 2/3 think this is true, when it's totally false. Now, who is this general public? Well, the average age was 38. There's half male, half female. And 80% of them hold some form of a college degree, from an associate's degree to a doctoral degree. So these are general public. These are like purely the general public we see. So how might they have been so misled? How could they be so wrong? Well, because there's mixed messaging here. There's mixed messaging. There's different messages that are coming out here. So let's look at some of the mixed messaging that has taken place. Just a quick reminder, this organization is run totally by volunteers, but we do have to pay for the production work. If you could help us out by going to give.jesusandscience.org, we'd appreciate it, or you can click in the description box below. If you can't give, we certainly understand, but please just give us a thumbs up and click subscribe. Thank you. So Professor Jack Szostak, who was at Harvard, who is now at the University of Chicago, who is a Nobel Prize winner. He's won a Nobel Prize. And he said in 2014, it says here, and this is just a direct cut and paste into here. It says, "You heard it here first," announced World Science Festival moderator and astrophysicist Mario Livio, as Harvard biologist and Nobel laureate Jack Szostak told a Search for Life gathering of 50 on Saturday afternoon in New York that he expected to make life in the lab in 3 to 5 years, and more likely within 3 years. He expected to make life in the lab in 3 to 5 years, more like 3. That was in 2014. Guess what? He missed his target. All right? Here we're 10 years into this, he's still not made life. Harvard astronomer and Origin of Life initiator Dimitar Seselov, also a panelist, told the audience that years ago, origin of life was a neglected question, mostly because people thought it was too hard. But outside the meeting room, he confirmed that they were indeed now very close to life in the lab. Seselov thinks it will take 5 years, not 3. All right? That was the message that came across. Here is to a professional meeting what Professor Jack Szostak said in 2021. And it's summarized here. He has not yet even made RNA in a prebiotically relevant manner. So what he says is, quoting him, and basically that's because RNA, and we know we had to get to RNA. And RNA is delicate. It also has a phosphodiester backbone. It is subject to degradation by intramolecular attack of the 2' hydroxyl on the phosphate. So you can get cleavage of the backbone, which is catalyzed by metal ions. So we don't have millions of years. Everything has to actually happen pretty quickly. The synthetic processes have to be faster than the degradative processes. That's true. That's the truth. RNA is very unstable. RNA, many people think that RNA is this key, that usually RNA is templated from DNA, and then RNA carries that message and starts making the proteins that build our body, the enzymes that build our bodies. And that's why you can, you eat a piece of steak tonight, and by tomorrow, the amino acids that made up that steak were degraded and then rebuilt into new proteins that make up a part of your body. It's because nature has these little things called enzymes, which are predominantly themselves polyamino acids, polypeptides, and do this. But what he's saying here is that RNA is really unstable. He hasn't even yet made RNA. It's a bazillion miles from RNA to life. He hasn't even made the RNA. Yet in 2014, he was saying they're very close. They'll have a life in the lab in 3 to 5 years. You see the mixed messaging? What he told the general public, what he confesses to scientists. That's the mixed messaging. Dr. Stephen Benner, formerly a Harvard professor and now director of the Foundation for Applied Molecular Evolution, said to a YouTuber in 2021, and you can go to that link and you can see it. He says, "I suppose many of the big paradoxes in origin of life have been solved." Many of the big paradoxes. So that presupposes that the little paradoxes have been solved. He's not even close. No way. No way. Well, what did he tell the professionals? So this was in 2021. What did he say at a professional meeting in 2019? Here's what he said. "Chemistry is actually hard to get to work. The molecules precipitate, the molecules hydrolyze, the molecules decompose. And so it's pretty much a constraint that you have to deal with. It's one goddamn problem after another." That's the truth. That's the real problem. Molecules don't want to come together. They decompose, they fall apart. What he told the general public to a YouTuber he was making these comments, and you can listen to this. I mean, the whole thing was a critique of Jim Tour and how wrong he was. And so you can go back. So I've challenged him on this, and he stopped stopped saying that most of the paradoxes have been solved. He stopped. And but this is what he tells the general public. This is why the general public is so confused, because they hear one thing and it's really another story. Professor Cronin, in a TED Talk, it was posted September 9th, 2011. Lee Cronin said, "What I'm going to try to do in the next 15 minutes or so is tell you about an idea of how we're going to make matter come alive." In 15 minutes, he's going to tell us how we're going to make matter come alive. At the end of his talk, the host there, Chris Anderson, said, "Just a quick question on timeline. You believe you're going to be successful in this project? When?" That was the question. Here was the response: "Hopefully within the next 2 years." That was in 2011. Guess what? He missed his deadline. Not even close. Not even close. So sadly, comments like this from researchers are misleading to the public. Researchers will sometimes blame the press. Now, the press can turn things up a bit, but what I have seen is that when the press doesn't understand something, they often will ask the scientist, "Did I get this right?" Right? Now, sometimes they get away with themselves and things come out. But it's the researchers. These are the researchers saying these things. This is why the general public is so confused on this area in the origin of life. Think about it. We don't even know where life has come from. Scientifically, we don't know how the first cell formed. You may say, well, it came from outer space. I'm good with that. It came from outer space. We're not talking about origin of life, but origin of first life. Where did it first come from? If it came from another, how? This is what we're talking about. We don't even know. All three of these researchers have more recently backed off using these inflated statements. And I think because people are calling them on it. People are making YouTube videos and calling them on it. Because those were inflated statements from the researchers themselves. The real state of origin of life research. So what's the real state here? Well, let me go over that with you. And remember, I am inviting my origin of life colleagues to critique me on this. If I say anything wrong, have at it. You come on my YouTube channel, go on anybody else's YouTube channel and say Tour was wrong with X, Y, and Z. I spoke in this same August Apologetics, I think it was in 2019. In 2019, when I got done, one of my colleagues from Rice University was attending, and he said, attended the talk. He was a physicist himself. He says, I was attending the talk with a biochemist from Baylor College of Medicine. He told me that you had several things wrong. I said, okay, well, we're not stopping there. I want to know what I had wrong. So he put me in contact with him. I said, what did I have wrong? And what he did is he cited a book, a textbook this thick on biochemistry. And I said, no, none of these games. Textbook, start looking through. What page in that textbook? I will get that textbook. I want to know what I said and what's in that textbook that I had wrong. I said, Rice University Library does not have that book. I am ordering that book. And then we are going to get together and you are going to show me on what page I had that wrong. I got an email back from him. He said, if you've already purchased the book, I will reimburse you. I'm not going to meet with you. What does that tell you? They don't know. They flat out don't know. And they can say over and over again that I am wrong. But they're confronted with this now. Where am I wrong? So I'm going to give you the real state of the origin of life research. And tell me where I'm wrong. So my colleagues out there, you're going to see this on YouTube. Tell me where I'm wrong. Nobody has shown a method to make enantiomer versions of carbohydrates, amino acids, nucleotides, or lipids in a prebiotically relevant manner. all these building blocks of the building blocks. Nobody has done this in a prebiotically relevant manner. You can do this with modern synthetic techniques in your laboratory. It's hard. It's hard. But in a prebiotically relevant manner, no way. Nobody has ever done that. You can get gross mixtures, and so they're never enantiopure versions, where you have one-handedness and not the other. You may say, well, maybe it just started with the mixtures of them. Well, we'll see on the next slide the problem with that. But these are so hard to make. And generally, where you find these, you can find certain sugars. You can find certain sugars coming in on meteorites, but the enantiomeric excesses are never high. I think that they've found amino acids, and not what the essential amino acids. I think the highest was like 70% enantiomeric excess, which means that you have so if it's 70% enantiomeric excess, it means you have 15% of the wrong isomer there, and that would cause you real problems. And so it's 15% because you double that number is the 30%, and that's what gives you the 70. It's a simple little equation, but in any case, and that wasn't even a valid amino acid. What happens is that these are usually gross mixtures of many compounds that are unusable, but we'll get to that in a moment. So nobody's ever made the building blocks of the building blocks. And if I'm wrong on this, show me the paper. Just show me the paper where people have done this in a prebiotically relevant manner. Nobody's ever shown that life could form with lower enantiomeric excess mixtures, thereby mitigating the need for chiral-induced spin selectivity. So chiral-induced spin selectivity has only been known for about 25 years. It's a new phenomenon that says that when an electron is going down a chiral environment, meaning say like a helix, it's going through a helix, it goes through better in one direction than in the other direction, because all electrons have a spin. They can either be spin up or spin down. That's the way they are. They either spin up or spin down. You have to match the spin to the environment of the helix, whether it's a right-handed helix or a left-handed helix. Because if you don't do that, they backscatter, and that generates heat. So the amazing thing is that we can use our brains to do all these processes, and we don't burn up. We don't burn up. My computer gets very, very hot, and I'm not even touching the processor chip. It gets very hot. Why don't our brains get that hot? Well, they'd fry if they got that hot. But how do they do it without burning up? Chiral-induced spin selectivity. This was not known 25 years ago. You had to have a chiral environment for life to start, because it would have burned up otherwise. It never could have gotten going. You had to have these in near enantiopurity. You could not have used the gross mixtures. This is what chiral-induced spin selectivity is showing us. So this idea that nature started with just racemic mixtures and it purified after that, that's not true. Nobody has ever shown that the mixtures found in meteorites or interstellar space could be useful for synthesis. Now, meteorites can deliver things. Generally, they burn up on the way in. But if they're buried deep inside that meteorite, sometimes the meteorite can hit Earth and some organic compounds can be spewing out. But there's not much of them, and they are in mixtures of all sorts of things. Now, when you take your vitamins and your supplements in the morning, you can take a whole handful of pills and eat those, and just take those all at once. And your body knows exactly what to do with them. It separates each one of those components, because your body has these little nanomachines in it called enzymes that pick these up and build our bodies. Biology is extraordinary this way. But chemistry cannot do that. In chemistry, we have to use pure compounds. Everything has to be really pure. Because what happens is it gums up the works. It gets in the way. So if you have an OH group on a sugar and an OH group on an amino acid, and you're under conditions that OH groups react, the chemistry doesn't know which one to do. There, I see an OH there. See, everything's a terrible mess. Biology can deal with mixtures. Chemistry cannot. And so that's why even John Sutherland, he was one of the people on that list, has said, I don't think meteorites make the right sort of mixture. But we need to have more constrained chemistry to actually make the right sort of mixtures. You have to have mixtures that don't conflict with one another. And everything that comes in on a meteorite is always in a mixture of many other things. It would be unusable. Someone would have to separate those. Nobody has solved the mass transfer problem in chemical transformations from small molecules to a cell. So, hey guys, if I'm saying something wrong, you're going to have to call me out on this. And you got to be very specific. And so the mass transfer problem. So remember, you need to go from these building blocks of the building blocks to the simplest cell, and the simplest cell is going to have to show all of these traits. Now, what happens in a chemical laboratory? You take some starting material, say you take 10 grams of material, and you bring it on to a new material, and now you've gone from 10 grams to say 5 grams, if you had a 50% yield, and considering that the molecular weight's the same, because I don't want to get into moles, because people forgot what a mole is. So we're just going to deal on grams, but it's a good approximation. So we go from 10 grams now to 5 grams, because I only got a 50% yield. Now I bring that on to the next step, and now I got another 50% yield, so now I only have 2.5 grams. And I do it again, and I have 1.25 grams. So after a few steps, you run out of material. That happens all the time, especially as you're exploring new reactions. Now, imagine on a mindless early Earth. It doesn't have a mind. It doesn't know how to optimize reactions. So it's going to use up a lot of material just doing junk, just going to junk. And you say, well, then it can go back. No, most of these reactions aren't going to go back. Very hard to bring many of these reactions back. And you say, well, it has lots of time. Okay. I'll give you, what would you like? You want 500 million years? We'll take 500 million years. So for 500 million years, you're going along. Now you've run out of starting material. You got to go back and make some more. Well, how'd you get to that point? Well, if you were in a laboratory, you'd have kept the laboratory notebook, and you know how you got to that point so you could reproduce it. But this poor mindless early Earth, for 500 million years, took to get from here to here, and now it needs to make some more. And it's like, I don't know how to do that. Well, why not? Well, because I never kept a laboratory notebook, because I don't have a brain. I'm just a mindless early Earth. There's no record of it. So you run out of material. So how much of material would you have to start with to build all the structures that you need for a cell? A gram of each certainly wouldn't be enough. A kilogram wouldn't be enough. A ton of each of these small molecules. And remember, there's lots of different sugars. There's lots of different amino acids, and we have multiple different bases that are on it. Where are you going to get these tons? They're not coming in on meteorites. They're not coming in pure forms that you can do it. And they need to be in a high purity form to be usable. This is the mass transfer problem. How do you get from here to here? How do you transfer this mass? You need to start with tons and tons of stuff, even if you had a mind. How'd you do this on an early Earth? You know what origin of life researchers say about this problem? Nothing. They say nothing. Because it's unsolvable. Nobody knows. That's why I wrote, nobody solved this. Nobody knows. Nobody has solved the amino acid polymerization problem with amino acids bearing active side chains. So here's the 20 amino acids. About half of them, all those in a solid red circle, are very reactive side chains, meaning that these side chains, so amino acids have an acid group here and amine group here. But some of them have functional groups like OH or SH hanging off them, and those are reactive side chains. The problem with that is you want the amino acid to form between an amine group on one and a carboxyl group on another. And what happens is these interfere. So say I want to hook up like this, all right? But if there's another piece coming out that can interfere, that interferes, and that ends up hooking in. That's the problem. That's the problem in all of these. So nobody has ever made a polypeptide where they've had the unprotected side chains and controlled that problem. There are ways to do that chemically in modern laboratories. You protect one end, you deprotect. It's a lot of work. But nobody's been able to do this in a prebiotically relevant manner. They've not been able to make the proteins. They can't polymerize these. And this is why I've presented to them, all right, how about we lessen the problem? I'm not asking you to make a polypeptide. I'm not asking you to hook a bunch of amino acids together. Just two. I want you to hook 2 amino acids together to make what's called a dipeptide. Now, most peptides, most enzymes are like 200, 300 units long. 500 units long, sometimes 800 units long. I'm just asking you to do one coupling, hook two of these together. And do this in greater than or equal to 90% yield. You say, why greater? Because if you don't have that kind of yield, what happens is the byproducts get in the way. And after a couple steps, it'd be no good anyway. And I presented this to those individuals that I showed you their names. I presented it to them as a challenge. I said, could you even make a dipeptide? You know what answer I got from them? Nothing. No answer. Remember, no answer is an answer in itself. They wouldn't answer. Somehow that's below me. Oh, you didn't know. There's no answer to this. There's no way to solve this. We can't even put two little things together. All right. Nobody's ever solved the nucleotide polymerization problem. So they'll take a nucleotide and they'll say, well, I can leave this on a rock and I get the polymer, but you get the 2,5 linkage. So this is the 3' linkage. This is the 2' position. So you see the little bit of difference here. This is hooked on this side of this 5-member ring. Here's hooked on that side of that 5-member ring. And you're like, that's close enough. No, it's not. It's not close enough. And these end up polymerizing off the side chain. So how can you do this? How do you solve this? It's hard. Nobody knows. So I've presented this to them. I said, just make me a 200-mer and less than 2% of the 2,5 linkage or the branch, because if you have 2%, that's 1 in 50 is going to be off. That'll never work. You know what answer they gave me? Nothing. No answer. They didn't know. They couldn't do this. How about the sugar problem? Sugars are the hardest molecules to deal with. So hard. So this is glucose. You say, how can you, if you had, say you had 6 entities, say you had 6 letter A's, what's the way you could hook these together in a string, just a linear string? Let's not talk about branch, just a linear string. It's only one way, A. That's it. All right, that's the only sequence you can have. But if you have 6 glucoses, do you know how many ways you could hook that together? You can actually hook that together. It's over 1 trillion different ways. 1 trillion. You know what a trillion means? Trillion is a big number. A million, if we put it in our time frame, 1,000,000 seconds is 11 days. If you go to somebody and say, will you marry me? Wait 1,000,000 seconds. Okay. I'll wait 11 days. If they say, wait a billion seconds, that's 32 years. I'm not sure I can do that. If they say, wait 1 trillion seconds, that's 32,000 years. You feel the difference between 1,000,000, 1 billion, and 1 trillion? This has over 1 trillion ways of just hooking together 6 of the same units, because they have all of these different tentacles. So they can hook up all of these different ways. And these can be open forms or closed forms. They can be 5-member rings or go to 6-member rings, like we're seeing here. How do you hook together sugars? Because you got to make polycarbohydrates, polysaccharides. How do you make these? Nobody knows. Now in nature you find enzymes. It's amazing. That can hook these together very selectively. The problem in my life is that people don't see what I see. Is that I look at a carbohydrate and say, this is amazing how nature can string these things together. And most people don't even worry about this. They just go about their lives and their carbohydrates hook together, and they don't realize the amazing things that are happening in their bodies, the selectivity that is occurring. Because if the carbohydrate structure gets wrong, it has been written, it has been published that every disease can harken back also to a carbohydrate problem, where the hookup of the carbohydrates is wrong. Every disease. You got to get this thing right. You got to get it right. Nobody knows how this comes together. And so that's why I ask them, okay, let's not make a polysaccharide. Let's just make a disaccharide, just 2 of them. Can you hook together 2 glucose molecules in this form, in 90% yield? Because remember, if you have 10% of impurity, that gums up the works totally for the next reaction. I presented this to them. And guess what their answer was? Nothing. They couldn't answer it. This is pretty humiliating, isn't it? I mean, you say you're going to have life in 3 years. You can't even put together 2 glucoses. You got to put together thousands of these. How could you have claimed life in a prebiotically relevant manner? You see how wrong it was for them to say these sorts of things? You can't even make a disaccharide. All right, here's the other problem. Nobody has solved the polymer stability problem when dealing with single molecules. Time is enemy number one. So this idea that nature has all sorts of time and you have all sorts of times you can solve these things because nature has lots of time. Nature doesn't have lots of time. Time goes away. Time is a problem for us. You say, well, 14 billion years is the universe. All right, I'll give you 14 billion years. But everything decomposes. And you say, well, how fast does it decompose? What you can do is you can take the half-life of a system and you convert it to a probability. It's a very simple calculation. But that tells us if we have a 600 mer of RNA, that's a very short RNA, that would last 4 hours. If you have one molecule of an RNA, not a mole, but one molecule, that lasts 4 hours in water without metal ions being around. Metal ions, this would last minutes. You have 4 hours. Okay, so if one RNA happened to form somewhere under a rock, somewhere on an early Earth, okay, now what? You're going to bring in all the reagents? You got 4 hours before that thing's gone. Time is enemy number one. A 200 mer polypeptide has a lifetime of about 13 days. 13 days is the twinkling of an eye when you're talking about geological time frames. All right, nobody's explained the requisite protein folding problem. So here's the problem. Proteins, once you hook together these amino acids, they have to fold up into the proper shape. Say I take a rope. I could take a rope and I say the rope is, say, 100 meters long, 100 meters long rope. And I say, I want you to weave this so that you make it into a hammock. Well, you can look up on YouTube, you say, how can I make a hammock out of a rope? And you can look it up and it'll tell you how to weave it. And you weave that thing, right? And you could do that. But what if you couldn't touch the rope? It just had to do that by the wind and the rain. It had to make a hammock. It's not going to do that. That's the protein folding problem. Proteins have to be in a particular shape to work. So the proteins come and then they form a shape, and that becomes the pocket in which these little reactions work in our body. All our enzymes function in these little pockets. And so what these authors write, even if you had 100 mer, 100 units long, amino acids long, you'd have 10 to the 95 possibilities. Now, if you're over 10 to the 40th, there's not enough time in our universe to do it. And they even write, even a small protein that initiated folding by random search at the time of the Big Bang would still be thrashing around today. Proteins need other proteins to help them to fold. So we'll use another protein. Okay, well, where'd that one come from? And where'd that one come from? That's the problem. There's another problem that's even more massive than that. That is the non-covalent interactions between all the molecules in a cell. Not the covalent, not where they're hooked together with a bond, just the way they relate to one another through non-covalent interactions. These are called van der Waals interactions. It's estimated that in just the protein, we're not talking about protein DNA, we're not talking about protein RNA, which is just protein interactions in a single yeast cell, which is a simple cell, that has 10 to the 79 billion combinations. You have no idea how big 10 to the 79 billion. That is one with 79 billion zeros after it. That's how many combinations. If this number instead of being 79 billion is 40, that's longer than the entire universe could solve that thing in time. 10 to the 79 billion is unsolvable. We don't know how these molecules align in a cell, but we know once you have a cell, what happens is the information parts to both sides, and then the cell breaks down in the middle, and now you have your two cells. The cells divide. So they've taken that inherent information, that alignment, and they've spread it to both sides, and so now you have your daughter cells. So that's how, once you have life, but where'd the first life come? Nobody knows. Nobody solved the code problem. You have to solve the code problem. So in DNA, it's a code that is the prescription for life. But it's much more than just DNA. There are modifications in the DNA that happen over time. There are modifications in RNA that then occur over time. And then many things are stored information in polysaccharides or polypeptides. There's information. This is how cells recognize each other. They'll have some of these sugars on the surface of the cell that recognize. So when two cells hit up, how do they know what kind of cell it's bumping into? How do they know? Because they look at they have sensors that detect the different carbohydrates that are on the surface of a cell. It's just amazing. What is happening in your body right now is utterly amazing. And you're blissfully unaware. But it is amazing what is happening in your body. Nobody knows where the code comes from. Nobody knows. It's not inherent in the cell. Nobody knows where that first code came from. Now, some people say, well, cells were very simple back then. They weren't like the cells that we have today. Actually, the earliest cells that we can find evidence of in the fossil record are about as complex as our simplest cells today. But these people have calculated that. Biophysicists have calculated, here is all the pieces that you would need to have a functioning cell, the simplest cell. DNA replication, repair, restriction, modification, basic transcription machinery. You have to have all of these different components. Do you know how many of these have been made in a prebiotically relevant manner? 0. None of them. None of them. So how could anybody claim that we're going to have life in a few years? How could you do that? So, professors Cronin, Benner, Sostek, Joyce, Sutherland, Lane, Lancet, Deemer, Reichert, Lipschitz, Hood, Krishnamurti, Devaraj, and Pauner. Come, let's reason together. What do you see that I'm not seeing? Let's reason together. Come, and we'll talk about it. We don't have to have a debate. We will just have a civil discussion and let the world see. You take your model. These are different models that the world has. There's the RNA model. Some people say RNA form first. Some people say proteins form first. And here's the supporters of these different models. Some people say metabolism formed first. Some people say the lipid formed first. Nick Lane says it all happened in a hydrothermal vent blowing out of the bottom of the ocean. And then there's these other ones that people have forgotten. And you choose any model you want. Any model. I'll give you any model you want. And I'm speaking to those gentlemen that I just cited their names. What do you need to make it simple cell? You have to have all the small molecules. Nobody's ever made these. So what I'm going to do, generous, I am giving all of you gentlemen these small molecules. All of them. Just assume you have these in complete enantiomeric purity. And now you just have to make the polymers of those. But you can't make the polymers. You can't even make a dimer. You can't even stick two of them together. You can't even put two together. So what I'll do, I'll give you all of those. I'll give them all to you in any sequence you want. So I'm giving you the code because it's the sequence of them that provides the code. It's a string of letters that are either random or there's a code there because they're forming words. I'm giving you the code. I'll give you all the... So we can actually take a cell. You can take a cell today and deconstruct it. You can take the lipids, put them in one bottle. You can take the nucleotides, put them in another bottle. So we'll just take a cell and we'll break it apart and I'll give you all of those. So my question to these researchers is, assuming you had access to all the parts, not in a hydrothermal vent in the bottom of the ocean, not under a rock, not in a puddle on the side of the ocean, assuming you had them in your lab, all nicely in clean bottles in your lab, could you assemble those into a cell if you had all the parts? And I already know the answer. The answer is no. And none of them is going to come forward and say they could do that. None of them. So how could they have said that they have made life? Even if I gave you all of the components, it's like if I gave you all the parts of the engine of your car. And you took all those parts and you dumped it into the front seat. Is that car going to run? No. You got to be able to assemble those and put them together. Well, how do you assemble something when there's 10 to the 79 billion combinations of non-covalent interactions that you have to align? How do you do that? I don't know. Nobody knows. We are far from this. This is what you're going to get. Crickets. Crickets. They will say nothing. They'll say nothing. They won't respond. They'll say nothing. But there'll be ad hominem attacks. Tour is a creationist. Did you know that's the last derogatory term that they're allowed to use in the university. They can't talk about my religion. They can't talk about my ethnicity, but they can call me the dreaded creationist. Have I talked at all about creation in this? I haven't mentioned any. It's just science. But they will use the term creationist and therefore think that they don't have to address this because he's a creationist. Has science explained the origin of life? Not even close. Science might explain it someday, but that day is far from today. I would never go and say that we'll never figure out how to make life. I would never say, because as a scientist, I can't prove the negative. You might be able to say, I can't say that because I don't know. If you asked a man in 1600, will we ever be able to land on the moon and come back again? They'd be like, no way. You can't even fly. How are you going to have space flight? You don't even have, you can't even, go 100 yards. I mean, you can't do anything. Things change. Humankind changes. Today, we're nowhere close. And the reason I can say we're nowhere close rather than, will we solve it tomorrow? I can tell you we will not solve it tomorrow. That I'm sure of. Because we're getting further away from a solution due to our increasing realization of the complexity of the cell. So the cell is not evolving in complexity. It's just that every year we recognize things about the cell that make it more complex for us. 25 years ago, we didn't know about chiral-induced spin selectivity. Now we know, and we go, got to solve that one too. Now we know about different systems level. It is not just embedded in DNA. Here, there's articles coming out now that DNA is no longer the code of life. There's so much more system level behind it. And for those of you that work in the computer industry, you will know what I mean, the system level behind it. And so this is what we're realizing now. So what's happening is the goalposts are moving further away. We might get a little bit closer, but this has gone 100 miles away. And I get a nanometer closer, it's gone another 100 miles away. Because the target is becoming more complex because we realize the complexity of the target. In the 1800s, they thought a cell was just a bunch of protoplasm. Now we know it is a factory in there, an amazing factory. So here's my appeal to the origin of life researchers. Here's your name. Here's my appeal. If we are beset with so many barriers, regardless of the model, you choose any model you want, why don't you join me in sharing the obvious with the press and the lay public? We have no idea how first life originated. Join me in saying it. Just say it. Say it. It's obvious that life can be made from inanimate materials. We know that. We are evidence of that. So there's nothing profound in that assertion. We already know by ourselves that life can be made from non-living materials. Life can be made from non-living materials because we exist. We exist. There must have been a time when there was no life, and then there was life. So to say that, well, we just need to answer, can life be made from inanimate materials? You're looking at it. I mean, that we exist is the testimony of that. So there's nothing profound in that. The problem is that any materialistic model that we invoke is far from having an experimentally verifiable hypothesis as to how life might have originated. All proposals fall far short. We cannot even solve a dipeptide. 2 amino acids hooked together. We can't even solve a disaccharide. 2 sugars hooked together with our prebiotic chemistry. I mean, this is like we're in kindergarten. So what should origin of life researchers do? Well, there's a lot of targets. Rather than going around saying you're going to make a cell, how about try to solve the mass transfer problem or get prebiotic processes to go in 100% yield so you don't have mixtures. The Leventhal 1.0 and 2.0 paradox, the protein folding problem and the interact, try to solve that one. The making of a certain, just try to solve the dipeptide problem. That'd be a good place to start using prebiotic chemistry, or the disaccharide problem, or make the RNA. Or remove the human intervention. Try to do those steps in your lab. Just leave the chemicals there and see what happens. Or you want to the secret to synthesis that can repeatedly survive impure mixtures. See if you can get prebiotic chemistry to work on impure mixtures. You guys make everything so pure. Where are you going to find that on an early Earth? Solve the relay synthesis problem, which we didn't even get into. Solve the condensation polymerization. So all of these polymers, they want to go back to starting material. The free energy is positive, which means that they don't want to polymerize, they go back. That's why they're so unstable. In just 4 hours, the thing is broken down. So it's the polymer stability problem. The origin of specified information. Where'd the code come from? Solve that one. And the final assembly. Try to work on that one. These are hard problems. So now I'm going to take a turn here, and I'm going to wrap up with some things. And again, I'm speaking to my colleagues out there. I want you to think about something different. We don't know how life originated. We don't even properly know how to define life. We know the characteristics of life. But life is an amazing thing. I want you to consider, what do all academic religious scholars from all religious backgrounds agree upon? Here's what they agree upon. Jesus died by crucifixion. Some even suggest that it is the most solid fact of that period in history. And these are not just Christian religious scholars. These are of any religious background. If they are academic scholars, they will all agree the evidence is there. That there was a person named Jesus that died by crucifixion, and they say from that era, that is probably the most solid fact from that era. They will also say the disciples of Jesus asserted that Jesus rose from the dead and that he appeared to them. Many of those disciples died for that assertion. They're not saying that he rose from the dead. They're saying the disciples asserted that he rose from the dead and that he appeared to them. And number 3, certain unbelievers, such as Jesus' brother James, and even enemies of Jesus, such as Paul, asserted that Jesus rose from the dead and appeared to them. They too died for that assertion. That's what every academic scholar in a religion department will agree upon. Well, what did Will Durant say about the Gospels, about the reliability of the Gospels? So Will Durant was a historian, and for those of you who are my age, you probably read Will Durant in school. Will Durant wrote the story of civilization. It's like 8 volumes. It's like an encyclopedia, and he wrote it from the dawn of history right up until the mid-20th century. And you say, well, he's a Christian. He's not. He says of himself, he says, I'm still an agnostic with pantheistic overtones. But he's an expert historian. What did he write about the Gospels? Here's what he said. The contradictions are of minutia, not substance. In essentials, the synoptic Gospels agree remarkably well and form a consistent portrait of Christ. In the enthusiasm of its discoveries, the higher criticism has applied to the New Testament tests of authenticity so severe that by them 100 ancient worthies, for example, Hammurabi, David, Socrates, would fade into legend. So what he's saying is the Gospels are so accurate, the contradictions are minutia. They're not substance. What he's also saying is that the higher criticisms, which started in the 1600s, where they started critiquing the Bible and trying to criticize it and shoot it down. If any other document had been put through what the Bible has been put through, it would have faded into legend long ago. This is what he says. He wrote this in The Story of Civilization, Volume 3. That's that chapter called Caesar and Christ. He went on. He says, despite the prejudices and theological preconceptions of the evangelists, they record many incidences that mere inventors would have concealed. The competition of the apostles for high places in the kingdom, their flight after Jesus' arrest, Peter's denial, the failure of Christ to work miracles in Galilee, the references of some auditors to his possible insanity, his early uncertainty as to his mission, his confessions of ignorance as to the future, his moments of bitterness, his despair and cry on the cross. No one reading these scenes can doubt the reality of the figure behind them. How do historians gauge what would be valid? They gauge by the honesty of the presentation. And he's saying that if these men made this up, they would have concealed these things. This is what an expert historian writes. If my colleagues, my science colleagues, want to dismiss this, how would you like it if the people in the history departments in your universities dismissed all of the science that happens in your chemistry or biochemistry department? This is how historians gauge accuracy. And this is what he writes concerning the Gospels. He goes on. He says that a few simple men should in one generation have invented so powerful and appealing a personality, so loft an ethic and so inspiring a vision of human brotherhood would be a miracle far more incredible than any recorded in the gospel. He says they couldn't have made this up. It'd be a miracle for men to have made something like this up. That'd be more miraculous than anything in the Gospels, he writes. And he finishes with this: after 2 centuries of higher criticism, the outlines of the life, character, and teachings of Christ remain reasonably clear and constitute the most fascinating feature of the history of Western man. So here's my invitation. To the person that does not believe in the resurrection of Jesus, to all of my colleagues that I'm speaking to tonight, to the person that does not believe. So if you do not believe that Jesus Christ has risen from the dead, you send an email to their tour@drjamestour.org, and I will meet with you one-on-one by Zoom. If you live in town, we can meet together, and I will go over with you why I embrace the resurrection of Jesus Christ. All right? You contact me. Now, this is not for believers. If you believe in the resurrection, this is not for you. I can send you references on what to read, and I can tell you right now. Read N.T. Wright, Resurrection of the Son of God. I mean, that'll have a lot more than I could ever tell you. But this is to unbelievers. You got to be kind to me and realize that I meet with a lot of unbelievers. And imagine if I saturated myself with believers that wanted to hear this. People say, well, I just want to hear how you do it. No. You have to be an unbeliever, all right? Just leave this time for the unbeliever, and we'll do that. So reach out to me, and we will do this. That's my invitation to you. Let's close in prayer. Father, thank you so much for this time. We see that we are fearfully and wonderfully made. Thank you, Lord, for all that you have displayed to us in the intricacies of life. Glory be to your name, Lord God. Thank you, Lord Jesus, because in you all things hold together, and you have created all things just by the word of your mouth and by your power. And for you they have all been created. Glory be to your name, O Lord, for the glory of Jesus. Amen.
Come right down here in the center aisle.
So thanks. I mean, clearly the problems are insurmountable. So what encourages these scientists to continue in pursuit, and who funds their work with no hope of conclusion?
Well, there's a different answer for each of those. So what drives them to do this? I've projected. I said, your boss is not going to solve this. I've told the students, you're not going to solve this, and your students are not going to solve this. So all of you are going to die of old age before this is solved. But these folks go around and they convince graduate students that, we're a few years away from this. I think that people are wising up, and it's a fascinating question. How might life have arisen scientifically? It's a fascinating question. So I think fascinating questions drive scientists. Some people want for some deeper meaning, some conspiracy theory or something. I don't know. I have trouble figuring out in my own mind why I do the things that I do, let alone why other people do the things that they do. But who funds this? Well, 40 million euro, which is probably like, $45 million, has just been given to a group of people in Europe across several different countries, and it's like 30 different researchers, and they're going to use AI to help them solve this. It's not going to help them solve this one. and these things come around, and they have 10 years to solve this thing. They're not going to solve this thing. But people keep throwing money at it. There's a lot of foundations that throw money at this thing because it's a fascinating question. Yeah, so there's a lot of money still being thrown at it.
Since you started speaking about this topic, have you seen any shift in the general community of scientists, either chemists or?
Yeah, I think they're being a lot more careful about what they're saying. These guys aren't going around saying anymore that we're going to have life in the lab in 3 years. I mean, and in fact, to his credit, Professor Cronin has said, yeah, when I said it's 2 years away, that was wrong. He's confessing, and now he's coming around, and he has even said that what's amazing, everybody makes a molecule, they make another molecule. So you keep making all these. Where's it going? Nobody can make a cell because the information always predates and had to have come from something external to the cell. So now you have a scientific researcher where science has driven him to the point to say the inherent information has come from outside the cell. That's Lee Cronin, who has been a big proponent of origin of life and a big proponent in calling Jim Tour the creationist, but he's seeing the same thing that we're seeing. So I think that, yes, people are coming around and they needed to be called out, and I'll continue to call them out because I have nothing else to do.
Hey, Jim. Can you talk quickly about someone who might say, he's just using God of the gaps? And can you kind of briefly touch on how maybe they're using time of the gaps?
Yeah, so I haven't brought God into this, and I've never said that we will never solve this. That people will say, I said specifically, I think that we may solve this. I can't say that we won't, but it's nowhere close. Maybe in 500 years, 100 years, I don't know, but it's nowhere close. But they use time of the gaps where they will throw out an argument, well, given sufficient time, this will happen. That's a time of the gaps argument. You have no understanding for that because given sufficient time, everything decomposes. I showed you how quickly these molecules decompose. RNA has 4 hours. So they're the ones that use gap arguments, and it's been a big time of the gaps argument. Given billions and billions of years, this happened. No, it didn't happen billions of years. How? You can't just throw that out. So that's the contrast to this is that don't use a time of the gaps argument. And I've never said that we can't solve this, and I've never injected God. There's things we can solve, some things that we can't. And the things that we can't, next year we might solve. But the how we really got life, that's a big one.
Anyone else? More questions? I'll meet you down here.
Hey, Dr. Tour. Try to make this simple. It seems we have people of influence who are approaching this to try to disprove the possibility of creation. And it seems we used to have leaders in thought circles who had faith and wanted to leave room for it. How do we get back to having leaders in academia that actually speak from an acceptance of the possibility of God angle?
You know, it's an interesting thing that they're coming around to God without using the word God. For example, Lee Cronin has said there are certain molecular structures that could not have formed randomly. They have a causal history. They have a causal history. So you see they're moving closer and closer without stepping into that. And I've publicly said, Lee, you're really an intelligent design proponent now. I mean, when you say causal history, you're saying that there's something behind this, you're intelligent design. And I put a little mock-up thing of him standing in front of the ARC display at one of these Texas sites or something or another. So I think that they're coming around to this. When Lee Cronin says there was information that had to have come from outside the cell before you could have Luca, which is the earliest cell that formed, that ended up propagating the life that's here. So they're somehow backing into this very slowly. And then on top of it, I think the younger generation is more willing to accept certain things, to look at certain things and to say, look, we don't have any horse in this race. So for example, I can understand why a person like Steve Benner would go around, and it was asked of Steve at a meeting not too long ago. We were at a meeting and somebody asked him, I didn't even ask him, somebody said, okay, we have all these pieces, why don't you just put them together and make a cell? And he said, well, a career is 3.5 score. A career is 4 score, and I'm about 3.5 score into this, so I'll leave this to the younger folks. What? You have all the pieces and you know how to put it together? And so I think that what's happening is when somebody has worked for 40 years in a certain area and made a lot of claims, it's hard to back away from it. And I understand that. It's hard to back away. And I understand as a scientist, you like to make bold claims. I mean, I've made my own bold claims. But what happens in an area like origin of life, it's a really, really bold claim. I think that younger people don't have as much in this fight, and so they don't have as much to back away from, so that they're going to be prone to be more honest about this and to say, we're really not very close to this. We're really a long way off. And so I think it's coming because science has a way of being self-correcting. Science, people can make claims and then you can begin to check this and it begins to correct itself. And so that's the hope.
If we dismiss the prebiotically relevant element, where we just said, yeah, like do everything you can using all the elements of the lab, is anybody close to making a cell?
No. That's why I say we can give, if I gave you all the components of a cell, and we can get them because we can just take a cell apart. So it's not like we have to make them. You just take an existing, and in a separate bottle, in your laboratory. And that was my challenge to them. Could you do this? Crickets. They don't even go about trying. Some silly people have in the past said, well, if you have a lipid bilayer, a vesicle, you put the stuff in it. No, that's putting all the parts of your car engine inside the car. That's a car. Here's my car. No, that doesn't work. They know they can't do the assembly. When you look at DNA, and it's wrapped around a histone, I mean, it's crazy hard. DNA is 2 meters long, and it's a thin little string. You know what happens with fishing line? It gets in a knot. I mean, how does it keep that stuff from getting in a knot and getting all tied up? And it wraps around, and then it untwines certain things when it has to read that. There's all this molecular machinery. You look at this as a person who builds molecules, you're like, this is crazy hard. We're nowhere close to that. So no, they just don't say anything. They don't say anything because in a modern lab you can't do that. Even in a modern lab you can't assemble a cell. And it's not that you can get close. It's nowhere close. What a synthetic cell is people have taken living cells. So Craig Venter did this. You take a living cell, and what you can do is you can take the genome out of it. So you take the DNA out, and over here you take DNA from another cell, or you synthesize DNA in a DNA synthesizer in your lab, and you put that back in. And that will run the cell. The cell was already there, it was already running, but you've put in a new, it's analogous to taking the computer control chip in your car and taking it out. And then going to Intel and copying that chip, that design chip, and then taking that and putting that back in the car. I mean, nobody's amazed that the car's going to run. And that's what they call the synthetic cell. But you already had the cell, so you put in a new genome. And but the construction of all the parts, it's nowhere close.
That's good. Another question? Anyone?
So just one question, like they have spent like years of studying in this field. Like you also mentioned that like they have like a nanometer like progress. And definitely they, as researchers, I assume they publish some papers and like peer review one. Like have they make anything like scientifically valid and also worth mentioning?
Yeah, I mean, I think that they've certainly done things that are worth mentioning and scientifically interesting things. The vast majority of what they've done are not prebiotically relevant. They've started with things that weren't prebiotic, and they bring it up to one little point and they mix it all together and they say, but whatever is in there may have been found on an early earth. So it might have a tiny little bit of prebiotic relevance at one particular step. But everything surrounding it wasn't prebiotically relevant. As a scientist, I find it interesting. And But as a scientist, I'm all for blowing all sorts of money on scientifically interesting things. I mean, I just find it because you learn a lot of other things. But so I don't want to shoot down what they're doing, but I think they need to pull back. And even in pulling back from the claims, what will happen is people will have a much more realistic view, and they'll go in and they'll try to solve key problems. When you have professors out there telling you that this thing is essentially solved, like Steve Benner, many of the big paradoxes in Origin of Life have been solved, why do you want to go into the area? It's been solved. These guys have solved it. It's better to say what the truth is. Like, almost everything hasn't been solved. Come on in this field, and then you'll get new life and new ideas, radically new ideas to try to solve these things, because the old ideas just aren't working. And people will say, well, you shouldn't shoot down what they're doing until you have a solution yourself. That's not the way science is done. You check mechanisms, and if a mechanism is wrong, you point out that the mechanism is wrong, even though you don't have the right mechanistic answer yourself. You just point out what's wrong so that somebody else will say, okay, well, here's a route. So yeah, that's what I'm doing. I'm just pointing this out. My job is very easy. Yeah. I mean, Jack Szostak, one of the gentlemen on the list, that Nobel Prize winner, he said, Jim, if you would just join us, we'll figure this thing out. I said, Jack, you think a lot more of me than I think of myself. I don't think I got this thing figured out. So anyway, that's it. Thank you for coming tonight. Thank you for attention. God bless you.
Dr. James Tour, thank you guys so much.
If you're enjoying this series, give us a thumbs up and click the subscribe button, and that way you'll hear when we're coming out with new videos. There are no salaried employees in this organization. All the accounting, all the legal work, that's all done by friends of mine. The only thing that I have to pay for is the production work, and if you could help us out with that, I'd appreciate it. There's a link below where you can just click on that and help us in several different ways. Thank you.